Good evening. So good evening and good morning for some people, but so good morning for the speaker, who is early morning for her. So it's a very happy. It's a happy occasion that we have a second seminar by Nairita Pal. She is a scientist in Los Alamos in fluid dynamics group, and before that. She starts from Presidency College, BSc, MSc from IIT Delhi, then PhD from ISC, and then she has been, after that, she has been in Los Alamos as a postdoc, then now as a scientist. So she will talk on mixing in multiscale systems. Okay, so Nairita, all yours, please start.
Okay, so thank you, Professor Verma, for the introduction. So I will be talking about multiscale phenomena in fluid mixing. So I'll start with a broad overview. As is generally known, mixing happens when two fluids combine to form a homogeneous mixture. There are a wide range of length and time scales involved in the mixing process. For example, in the picture in the left, there is a dropping mixing in a glass of water, and mixing happens in the scales of a glass. Whereas in the picture on the right, we have volcano erupting, and the ashes mix with the atmosphere. So mixing happens in the scales of a mountain. Now, mixing is aptly called a multiscale process because in mixing, we have to resolve all the scales right from the system size down to the molecular scales, if possible. Now, there are experts of multiscale phenomena in the audience today. For example, this is a very nice review article, physically motivated review article, and is an excellent read by Professor Mohan Verma. Okay, so this is a slide which contains the summary of my research till date. I have primarily worked on two-fluid mixing and phase separation in turbulence. So I have worked on immiscible fluid mixing using direct numerical simulations, and I have worked on miscible fluids using analytical closure models of turbulence. And currently my interest is climate simulations, which has both DNS and closure models. That is, I'm studying simple mathematical models to study the climate. And these are some representative papers from each study. And in the interest of time, I will only cover a subset of these research works. So I will talk about immiscible mixing in turbulence, then miscible mixing in turbulence, and I will conclude with some future research plans. The binary fluid mixing or two fluid mixing can be of two types, immiscible and miscible. What are immiscible fluids? When there is a surface tension between the participating fluids, that is known as immiscible fluid mixing. For example, think of oil in water. So oil has a large surface tension in water, and for that reason, oil does not mix homogeneously in water. Rather, there are drops of oil in water. And then there is miscible fluid. When there is no surface tension between the two fluids, that is known as miscible. For example, think of ink in water. So the immiscible fluid was mostly my PhD research, and I did direct numerical simulations in that. And my post-PhD work deals with miscible fluids. So first I will talk about immiscible fluids. So as I said, in immiscible fluids, there are droplets of one fluid inside the other. So essentially, immiscible fluid is the study of droplets. So some practical examples, oil in water, and then we have cloud formation, where there are small drops of water which move in background air, and they merge together to form big cloud masses. So in essence, while studying droplets in air or in a background fluid, we have to track aerosols, water or oil droplets through the background fluid. Now, this is a multiscale process. This is a multiscale process because of the following two reasons. First, we are considering the finite size of droplets. That is, they are not point particles. And when the droplets have finite size, the radius can be orders of magnitude greater than the interface thickness. And so we have to resolve both the radius and the interface thickness. Secondly, if there is background in the, if there is turbulence in the background, that has many scales, and that also changes the interface shape. So we have to resolve all the scales starting from the system size right down to the interface thickness. And so this is a computational challenge. And most of the previous studies do not consider, do not resolve all these scales properly. And that is precisely what I did in my PhD. I studied droplets in turbulence using a phase field model. So this is a numerical model in which the boundary between the droplet and the background fluid is described by a PDE for the evolution of a scalar order parameter phi. So I will explain what this is, but in simple terms, actually there is no explicit boundary condition at the droplet fluid interface. So we do not have to worry about the boundary conditions. And this is a huge simplification for studies of droplets. And of course, in my study, the droplets have finite size so that there is two-way coupling with the background fluid. That is, the background fluid changes the droplet shape, and the droplet also affects the background fluid. And we use the coupled Kahn-Hilliard-Navier-Stokes to solve this system. I will explain what this is. And the numerical method is pseudospectral method. So this is the Navier-Stokes equation, which is the starting equation for all my research work till now. This is the advection term, which is responsible for all the nonlinearities in the system. Now, I will mostly talk about 2D Navier-Stokes in the first part of my talk. In 2D, there is a simplification because if we take the curl of the Navier-Stokes and the fluid is incompressible, then the pressure term drops out. And also the curl of the velocity or the vorticity is a scalar in 2D. So essentially, we have a scalar evolution equation in 2 dimensions. And this is an 8-man friction, which prevents the buildup of energy in the large scales. And this is special for 2D turbulence. So before going into droplets, I will talk about binary fluids and phase separation in binary fluids in general. So consider 2 fluids, A and B. A is the blue fluid and B is the red fluid, suppose. And this is an early time snapshot. And B, the red fluid, is dispersed homogeneously inside the blue fluid. Now, if we evolve this system using the phase field model, we arrive at this final state where the 2 fluids have completely phase separated. That is, there is a minimum number of interface between the 2 fluids. So essentially, the phase field model is capturing the interface dynamics. That is, it is minimizing the number of interfaces. So this is a movie from the simulation in the paper where it shows the 2 fluids are completely phase separating. So what is the phase field model? So in the phase field model, we take help from non-equilibrium statistical mechanics. we describe the whole system in terms of a coarse-grained order parameter field, phi. So this is a field variable because it depends on every point in space. Now, phi is actually the volume fraction of the entire system. That is, it has a value, say, +1 in the red fluid and -1 in the blue fluid. And so we can describe the whole system in terms of this single order parameter phi, and we do not have to describe the two fluids separately. This phi takes care of both the fluids. Now we assign a free energy functional to the whole system. This is known as the Ginzburg-Landau functional. So this is a functional because the output is actually a function. So this free energy functional has two terms, the bulk potential energy part and then interface part. So for the bulk potential energy, the simplest choice is a double well potential with the two minima occurring in the two fluids. Okay. So now the challenge is to find an initial condition for phi. To do that, we minimize the free energy functional with respect to phi. That is, we basically find the equilibrium solution. Now the minimization procedure gives us a tan hyperbolic function for phi. This tan hyperbolic function has two asymptotes in the two fluids. So +1 is in one fluid and the other asymptote -1 is in the other fluid. The important thing is that this function changes continuously in the interface. That is, there are no sharp discontinuities. And this is a great help for numerics because many numerical problems due to sharp interface can be avoided. So now that we have an initial condition for phi, which is tan hyperbolic, we need an evolution equation. So we impose the condition that the order parameter phi is conserved. And basically this means that the two fluids can exchange densities only locally. Now for a conserved order parameter field, again, going back to non-equilibrium statistical mechanics, the evolution equation is the Cahn-Hilliard equation, or what is more commonly known, it is the model B. So this Cahn-Hilliard gives the evolution for phi. The fluids are, if there is turbulence in the fluids, the velocity of the fluids should come from the Navier-Stokes. So basically we couple the Cahn-Hilliard to the Navier-Stokes and get a two-way coupled equation where the velocity of the Navier-Stokes is used to advect the field phi, and the field phi acts back on the Navier-Stokes in form of a back reaction or a forcing or a surface tension forcing term. So here the coefficient lambda gives the coefficient of surface tension. So this is like a forcing term.
Nairita, I have one question. So
sure.
Yeah. So I got a bit lost because when you are writing Navier-Stokes equation and Cahn-Hilliard equation, so Navier-Stokes you are writing for both the fluids or what? I mean.
Yes. So this velocity here is like a mean velocity for both the fluids. It is like a mean. It is the mean velocity.
So it is like the center of mass fluid actually.
Right. Exactly. It is the center of mass fluid.
And what is phi?
Here the phi is the volume fraction. You can say this is the order parameter field. So
you just defined there exactly.
Yes. Yeah.
Right. Okay. So okay.
And the velocity actually basically it can be that is a good question actually. I mean, if the fluids are incompressible, the velocity and suppose if U1 and U2 are velocities of the two fluids, this U is basically U1 plus U2 by 2. So it is just the center of mass or a mean velocity.
The arithmetic mean of the two. So, so in your formulation, the fluid is actually not incompressible, right? It is general till now.
It is incompressible.
It is incompressible. And where have you actually used this other? So have you used the divergence-less condition for the velocity? I'm just wondering.
Yes, so I have used the divergence-less condition. So firstly, this density rho is a constant. This should be rho 0, basically. If the densities were different, it will be rho 1 phi 1 plus rho 2 phi 2 by, and here the rho will be inside the gradient and things like that. Basically, the whole equation will be multiplied by rho.
Okay, sure, please.
This velocity is again, it has divergence U is equal to 0.
Also, your dissipation term does not have the term with the divergence U, so it is true that you are using compressible. Correct. Thank you.
Yes, exactly. Yes. So, okay. So now, how do we define droplets using this method? So as I said, the initial condition is tan hyperbolic. Now I just take a two-dimensional tan hyperbolic function and use the argument such that it is tan r instead of tan x or tan y. And to define the bounds on the radius, it is just tan r minus r naught, where r naught is the radius of the droplet. And this function has two asymptotes. One asymptote is in the background majority phase, and the other asymptote is in the minority or droplet phase. And the important thing is that this function phi changes continuously in the interface. So it is a diffuse interface method. So this is a snapshot of phi, which is the volume fraction actually. And now when we evolve this using the Canhillier Navier-Stokes, we see that it is advected by the flow. This is the volume fraction, so you cannot see the velocity vectors in the background, but the background is turbulent actually. Okay, so now some simulation details. The simulation box is periodic, and we use the pseudo-spectral method where the spatial derivatives are evaluated in the Fourier space actually. And for time integration, we use the second order Adams-Bashforth method. And we have our own codes written in the GPU-based language CUDA. And before that, we actually developed a parallel Fortran framework. Now, to digress a little, droplet dynamics is very important in today's age of COVID, where infection is spread via droplet transmission. Now, droplet dynamics has three stages: the center of mass motion of the droplet and the surface deformation, and then the droplet breakup, and then droplet size distribution. Now, I have worked on all three stages, but in the interest of time, I will only talk about the center of mass motion and surface deformation. So basically, I will talk about a single droplet in turbulence. And here, what are the input parameters to our code? That is, what do we specify? We specify the surface tension and the size through the diameter of the droplet. And the surface tension sigma is a simple function of the surface tension coefficient. And what are the what are the output that we look at? We look at two things: the droplet deformation and the droplet acceleration. So first, I will talk about the droplet deformation. Sorry. So first, I will talk about the droplet deformation. To do that, I define a deformation parameter known as gamma, which is the ratio of the perimeter of the deformed droplet to the perimeter of a perfectly circular droplet minus 1. Now we subtract 1 because the perimeter of a perfectly circular droplet is always the smallest. So this quantity is always greater than 1. Now, when we plot the deformation parameter as a function of time for 3 values of surface tension. In our original paper, we did non-dimensionalize the surface tension in terms of the Weber number, but I will not go in that detail right now. Basically, we did it for 3 values of surface tension. And as is expected, for the lowest surface tension, the droplet deforms quite a lot. That is, there are many high intermittent spikes in the time series of deformation parameter. Whereas for the highest surface tension droplet, there are no high deformations. That is, the droplet is not affected by the background fluid much if the surface tension is high. Now, this plot is in the statistically steady state when the mean has reached a steady value. Mean velocity has reached a steady value. And the deformation parameter comparison is clear when we draw the probability distribution function. The probability distribution function is actually like a histogram of the time series. So for the low surface tension droplet, the PDF has high tails because it has many intermittent high spikes, whereas the high surface tension droplet, which is like a rigid stone, it has very small surface fluctuations about a mean value.
Okay, Nairita,
So,
one small question.
Yeah.
Where does surface tension go into your equations?
So it is inside the back reaction term.
Okay.
So in the
lambda.
coupling, lambda, yes, lambda. So lambda is basically the surface tension is a simple function of lambda. This is found from a line integral and things like that.
Okay, thank you.
Yeah. Okay. So now I will move on. So now that we have discussed the surface tension, I will talk about the droplet acceleration. And now the variable is the size of the droplet. Surface tension is constant, say in the middle value, in the green value, and we only change the size of the droplet, that is the diameter of the droplet. And like in the previous case, there is a time series for the acceleration. Now the acceleration is a vector. In 2D, it has 2 components, x and y. But since the system is homogeneous, we just consider the y direction because the x direction will have a similar statistics. Since the system is isotropic, both directions can be considered equivalent. So we just look at the y component of acceleration. So in this plot here, this is a PDF of the acceleration time series of the droplet. So here the black line is a Gaussian fit. And the red, blue, and pink curves are PDFs for very big droplets. That is, these droplets have sizes which are almost about 1/3 the size of the domain. And this blue dots is the PDF for a very small droplet, which is about 1/10 the size of the domain. So this plot tells us that very large droplets have PDFs which are close to a Gaussian, whereas the small droplets depart strongly from Gaussian nature. Now, as we explained in our paper, this fact is because the small droplets show intermittency in the acceleration time series. And this intermittency arises because the small droplets get trapped in the big vortices more frequently than the large droplets. And yeah, okay. So these results are there in the paper. So with with this, I will end my discussion on immiscible fluids. It is worthwhile to mention that our results agree with previously published results of finite-sized rigid particles. That is, when the surface tension in our study is large, it agrees with results of previously published rigid particles in the work done by Jeremy Beck et al. And thus we can say that our method to study the dynamics of large particles using Cahn-Hilliard Navier-Stokes is a valid approach. So I will end with a short movie which shows contours of a droplet moving in a vorticity field. So the background is vorticity. The droplet also shades vortices, sorry. The droplets also shades vortices. So you can see the vortex shading at the ends of the droplet. Okay.
One question,
Yeah.
sorry.
Yeah.
So if I understand well, until now your analysis is based on 2D, right? So it is two-dimensional thing. So
Yes.
if I remember well, so I mean, when Prasad presented his work several times, so he said that there's a critical value for bubble to the background fluid. So I mean, is it the same case? So mostly in 3D, but in 2D, do you have also a critical value for that, so that the I mean, is the question understandable or?
Yeah. So basically, so he was talking about the bubble breakup, or?
No, he said that, I mean, if the number of bubbles or if the volume fraction of the bubbles with respect to the, background fluid crosses a certain value, then this type of analysis is no longer valid. That means you cannot say that bubbles are in a fluid. So you have some an embedding fluid and you have some bubbles embedded into it. So I mean, my question is, so in 3D he had some value, so in 2D do you have some critical value as well?
Yes, so yeah, right. I mean, this particular analysis is for a single droplet in turbulence, but yes. So what you are meaning is probably the following: that suppose in this thing there is a critical length scale where this phenomena of phase separation gets arrested. That is, there is a critical length scale of the bubbles at which it is a balance between the surface tension and the background turbulence forcing.
Exactly. So do you have this type of thing as well here in the 2D case?
Yes, so there is, so that is what we explain in this paper. Basically, there is a 2D counterpart, and that comes from dimensional analysis of the coupled Cahn-Hilliard Navier-Stokes, because in this case we have to consider that everything is two-dimensional, and so there is a corresponding dimensional analysis, because the energy scaling spectra also changes. It is key to the power -3 in 2D, in the 2D inertial range. So to balance that, it will the surface tension coefficient will have the bubble length scale will have a corresponding value. I forgot the value. I guess it is 2/3. I think it is 2/3.
I will check in the paper, but I was just wondering because he also said that the spectra is modified by that. That's why I asked the whole question. Okay, thank you.
Yes, the important thing is there is a balance between turbulence and surface tension. And yeah. So now I will start my discussion on miscible fluids. And this is mostly my post-PhD work. And I worked on turbulence models, analytical models in here. So before going into turbulence models, let me first talk a little bit about the closure problem of turbulence. So this is the Navier-Stokes equation in component form. Now we can decompose the velocities into a mean and a fluctuation part. The mean is a time average mean in the statistically steady state. Now, if we write the Navier-Stokes in terms of the decomposed velocities, and we separate out the mean flow equation, we notice that there is a problem, because in here, apart from the mean flow quantities, there is an extra quantity, which is the fluctuation, which is the correlation of fluctuating velocities. So here the mean flow quantities are already unknown, but we have an extra unknown, which is the correlation of fluctuating velocities. Now, this is the closure problem of turbulence, because here the number of equations is less than the number of unknowns. That is, we have more unknowns. We can write an equation for these fluctuating velocities, but then we will have a term which has a triple correlation of fluctuating velocities. So there is a hierarchy of equations, and this is the closure problem. Generally, this problem is solved by writing a model for these fluctuating quantities, and I will show how we did that. So my system setup is the following. I am studying buoyancy-driven two-fluid homogeneous flow. What this is suppose we have big blobs of an yellow fluid, which is the heavy fluid, inside a background lighter fluid. And suppose ink and water, but only one component is heavier than the other, and gravity is pointing downwards. So this system is homogeneous because the yellow fluid is homogeneously dispersed inside the domain. Now, due to gravity, the two fluids start mixing, and the yellow blobs break up into very small blobs eventually. So the kinetic energy increases, reaches a maximum at this stage, and then decreases. Now, this is a DNA snapshot. This is 1024 cubed simulation in 1000 processors. And it takes about 8 months for the DNS to start from this stage and arrive at this stage. Now, this is a huge computational cost. So the question we are asking is, can we have an analytical model which will capture the turbulence dynamics, but with a much lesser computational cost? So that is what we are going to do. We want to capture the flow characteristics using efficient analytical models. So to reiterate, the system is statistically homogeneous. That is, it is translationally invariant, can say, and the driving force is buoyancy. And as a note, the full DNS takes 8 months, but our model takes only 2 minutes, and it captures the essential turbulence dynamics of the system. So the model I studied and developed is known as a 2-point spectral model, or a local wave number model. So why is it a 2-point model? It is a 2-point model because variables like the correlation of fluctuating velocities, which is also known as the Reynolds stress, is a function of 2 points, x1 and x2 in space. Now, since it is a function of 2 points, this model can capture the natural evolution of scales. And this scale is defined by the separation x2 minus x1. And now this point is a very important point for turbulence models, because we have to remember that the Navier-Stokes system from which the model is derived is inherently a 2-point system. So 2-point models can best describe the evolution of a flow. And this model can capture phenomena like strong transients. That is, it can capture the process of transition from a laminar to a chaotic or turbulent state. This is a slide on more points on why 2-point models. So when we have very successful 1-point models like RANS models. So I have compiled 4 points. The first and most important point, as I said, is 1-point models has no information on length scale evolution, but 2-point models has information on scale evolution. And because it has no information on scale evolution, 1-point models cannot describe energy transfer or energy cascade. but two-point models can describe energy cascade and energy spectra. And because of this, one-point models cannot capture transients, but two-point models can capture transients. One advantage of one-point models is that the computational cost is lower, but in today's age where computation is becoming increasingly cheaper, it is worthwhile to invest in two-point models. Now, there is a big history on analytical, statistical two-point models, but the most successful two-point model is the eddy-damped quasi-normal Markovian theory. But this model also cannot capture two-fluid mixing. And this is precisely what I did. I developed a two-point model which can capture two-fluid mixing. And especially for variable density flows, that is flows which have large density contrast, and that is it departs strongly from the Buoyancy regime. And our model is known as local wave number model. So what are the variables that we study? Now, we studied the evolution of three variables in our problem. These are all statistical ensemble averaged variables, just to mention. So the three variables are the following. First is the density weighted Reynolds stress tensor. So this is the correlation of fluctuating velocities weighted by the density, since it is a variable density problem. And then we have the turbulent mass flux, which is the correlation of momentum and specific volume. And finally, we have the mix parameter, which is the correlation of fluctuating density and specific volume. So this mix parameter is very important in variable density studies, since it denotes how far the mixing has progressed. Now, as I said, our model takes 2 minutes compared to the 8 months in DNS. How do we achieve that efficiency? So there is a reduction in dimensionality in our system. And this is how we reduce the dimensionality. We define all the variables in terms of center of mass and separation coordinates. And then we take a Fourier transform of the variables. After that, we angularly average the variables in K-space, assuming isotropy. Now, after angular averaging, we go from a vector K to a scalar K space, and thus we have reduced the dimensions. Also, since the system is homogeneous and translationally invariant, we can drop the center of mass coordinate. So essentially, we have all the variables dependent on the scalar wave number K. So we went from a 3D system to a perfect 1D system, and which is more efficient. Now, these are the three evolution equations for the three variables under study. Now, the equations might look daunting, but they have a simple symmetry between them, in the sense that they have a force production term, which is the buoyancy production, and this is exactly derived from Navier-Stokes. The mass flux velocity also has a production term. The mix parameter does not have any production because there is no production of species in the system. And then there is a dissipation term, which is exactly derived from the Navier-Stokes again, a viscous dissipation and a mass diffusion. The term which is modeled is the nonlinear term. And this denotes the K-space cascade or the K-space transfer. And this is by far the most important term, which captures the energy spectra. Now, the K-space cascade is modeled as an advection and diffusion in K-space. And this cascade term has the same form in all three variables. That is, it has an advection part and a diffusion part. And the mass flux velocity has a drag term, which is not very important and important in most practical flows. Now, there are some modeling coefficients for the cascade term. These have rigorous theoretical derivations, and also after which we carried out a sophisticated optimization procedure to tune the model to match the DNS system. So basically, this is the final set of coefficients. And for this set of coefficients, we see that our analytical statistical model gives excellent agreement with DNS. So here, blue is the DNS curve and the orange curve is our model result. And this agreement is also obtained at a very high output number, that is output 0.75. We have checked that, and our model also gives this kind of agreement at output 0.05. Our results are in this paper, and for the same set of coefficients, basically. So to reiterate, the full DNS takes 8 months, whereas our model takes only 2 minutes and captures the essential phenomena, that is the transition part of and the turbulence part of the important quantities under study. Here is the kinetic energy. The decay part is not very well captured in the model, but that is due to the numerical diffusion in DNS, and we are trying to address that in future studies. And we see the spectral evolution is also very well captured. And now, inspired with the success of the homogeneous turbulence, we extended our model to study inhomogeneous turbulence. And here the system setup is a typical Rayleigh-Taylor setup, where we have a heavy fluid sitting on top of a light fluid and gravity is pointing downwards. Now, this system is inhomogeneous in the vertical direction. We call it the Y direction. And we cannot drop the center of mass coordinate anymore because this is inhomogeneous. And we have to retain the Y direction. But even then, the system is homogeneous in every plane in the horizontal direction. So basically, now we have a 2D system where we consider the inhomogeneity in the Y direction, but the system is homogeneous in every plane, and there is a coupling between the planes in question. There is a coupling between the homogeneous planes. So there is an extra equation for the coupling term, and this also comes from the nonlinear term of the Navier-Stokes. And we see that our model gives very nice agreement with simulation. Here the simulation was actually large eddy simulation, and in terms of the mix layer, and this is the mixing parameter in every plane, and this is the energy or the trace of the Reynolds trace tensor. So we get a very excellent agreement of the model against simulation. So these equations were formulated by us for the first time. Okay, so with this, I end my discussion on miscible fluids, and I go on to discuss some things about my future work. So the future work, meaning I am working on these things right now, and I wish to continue this work for the next 3 years or so. So basically, I am studying Navier-Stokes in the ocean using simple mathematical models. Now, Navier-Stokes in ocean also is important for climate models. How? The climate model has 3 important components. First is the atmosphere, then the ocean, then the land. Now, the ocean, which is mainly saline water, is by far the most important factor in global warming because it has the highest heat capacity. So studying ocean is very important. Now, of course, in predicting global warming, the whole system is very complex. That is, it has many components. But the ocean is the most important by far because it controls the transport of heat flux in the earth. by mixing. And this controls the climate variability of the Earth. So here, as I said, the ocean currents control the transport of heat flux by mixing. So basically, ocean currents control the temperature of the Earth. So here, basically, you can see this is a projection of the Earth system, and the arrows denote ocean currents. So the arrows denote ocean currents. Now, what are the factors affecting the ocean currents? First is the Coriolis force. And then we have tides, winds, and waves. These affect the mixing in the oceans and thus control the currents. And then we have the shape of coastlines also. And finally, the density difference. I am not considering density difference for now. I am just considering the tides, winds, and waves mixing. So the ocean dynamics framework that I use is a typical shallow water framework. A shallow water system is one where there is only one layer of ocean. So if there is only one ocean layer, it is known as a shallow water system. And this has the following approximations. First, the hydrostatic approximation. Here, pressure is a function of the vertical distance z. It is a linear function of z, and the density is constant. So first, we have the mass conservation equation, from which we get the evolution of layer thickness. Here, h is the layer thickness of the ocean. And then we have the Navier-Stokes equation supplemented with the Coriolis force. And here, due to the hydrostatic approximation, we can write the pressure gradient in this form. Now, we can write the nonlinear term in a vector invariant form. That is, the nonlinear term can be decomposed into a rotational part and a gradient of kinetic energy part. And then the Coriolis force is absorbed in the rotational part. Now, we do this trick because suppose if we change to a frame of reference attached to the rotating Earth, then the Coriolis force is not there. And the effect of the Coriolis force is felt through the rotational part of the nonlinear term. Okay, so this is the equations. These are two equations that we use. And these are some details on the mesh. Basically, we use a variable resolution multiscale mesh. This is multiscale because it resolves the processes at different scales in the ocean. And we did some verification tests like surface gravity wave. We found the velocity of surface gravity wave on an aquaplanet. An aquaplanet is a planet without any continents. And when we have a Gaussian sea surface height and just evolve it using the Navier-Stokes, we see that it diffuses and generates gravity waves. Now, we can find the speed of the gravity waves theoretically from the linear wave equation. And we see that our model gives, our simulation DNS basically gives a close agreement with the theoretical result. Now, it is not exact because Navier-Stokes is a nonlinear system, but this is the linear solution of the wave equation. Now, finally, as I said, I am going to study tides in oceans. Tides are generated from astronomical forcing, and they are periodic in nature. So they are periodic in time. And you can see with tides, the kinetic energy goes up and down periodically. And these tides, this up and down nature of tides control mixing and ocean currents. To understand mixing from tides, it is important to analyze the tidal harmonics. So what are the tidal harmonics? So tides are generated by the gravitational pull of the sun and the moon. Now, there are many gravitational constituents. about, say, there is a table of tidal constituents which come from which denote the effect of the pull from the sun and the moon. For example, the M2 constituent, which is the largest lunar constituent, it gives a period of tide about once every 12 hours. And S2 is the largest solar constituent. Similarly, it has a period. These constituents basically come when we expand the periodic function in a series. So due to series expansion, we get different coefficients. And we compare the dominant coefficients, actually. So we compare our simulation with satellite observations, and we see that the location and the amplitude and the phase of the constituents are very well captured in our DNS framework. And then what I am doing right now is I am studying the interaction of the Antarctic ice shelf cavities with the tides. Now, this is important because the tides change the melting rates of the ice shelves. So there is some thermodynamics involved in that calculation of how tides change the melting rates of the ice shelves. And also when the ice shelf melts, the geometry of the shelf changes, and that also affects the coefficient of the tides. And so there is a two-way coupling. So this is mostly my future work. And I will end with one more future research plan. In this project is very interesting to me, and in here I want to study microscopic fluctuations which drive macroscopic perturbations. Because we know in classical hydrodynamics, we need to provide a macroscopic perturbation to a fluid interface for the instability to grow. That is, it should have a finite amplitude for the instability to grow into turbulence. However, particle methods like direct simulation Monte Carlo, they can generate instability from thermal fluctuations of each particle. That is, they can consider each particle separately, and the thermal fluctuations can generate the instability. However, if we want to carry out direct simulation Monte Carlo for classical 3D systems, the time required would be astronomical. So I plan to use fluctuating hydrodynamics to generate the instability from a flat interface. And finally, I want to validate my results against direct simulation Monte Carlo. So to say something about fluctuating hydrodynamics, what is fluctuating hydrodynamics exactly? So it is basically Navier-Stokes with a thermal fluctuation term. And that thermal fluctuation term looks like a noise term, but the difference is it has a coefficient which is derived from first principles. That is, we cast the Navier-Stokes in form of a Langevin equation, and then we can obtain self-consistent coefficients from kinetic theory. So I have done these derivations, and I am formulating the simulation method, and then we need to verify against direct simulation Monte Carlo. Now there is a very interesting paper by Professor Mohendra Verma on the energy on driven dissipative systems. That is, in there, the energy transfer from large scale to dissipation scale is explained in detail. My research plan is kind of complementary to that, because I am now focusing on the drive term. That is, I am considering systems where microscopic fluctuations generate the drive term. And then there will be dissipation by viscous dissipation as usual, but the drive is not provided by any large scale forcing, but by thermal fluctuations now. So, sorry. Okay, so finally, these are the details of the HPC resources that I have used. I have used the Cray supercomputer in IAC, the NARSC supercomputing agency in the USA, and the supercomputers in Pacific Northwest National Lab and at LANL. And I have used shared memory framework in a single machine or a small cluster like OpenMP, and GPU-based languages OpenACC and MPI. And these are some journals that I have published over the years. And these are some conference presentations and acknowledgements in the reverse chronological order. And with this, I would like to end my talk.